Hello there, Mr. Sutton here, bringing you this AB Calculus 3.8 lesson on implicit differentiation. In this one, we will be finding derivatives of equations in which it is difficult or impossible to isolate y. And as a real-life application, we will figure out the slope of a moon's orbit. For your warm-up on this one, pause the video and take a sec to try to find dy dx, the derivative, for each of these equations. Alright, let's see what you came up with for part A. So for this one, we have dy dx equals the derivative of the right side here, 3x squared minus 1. So no problem, right? This is something we're used to doing. Now let's do part B. Wait a second. This is weird. We can't really isolate y. If we could get y by itself like it is in part A, then we'd be in business. But since we can't isolate y, maybe we're not really sure what to do in that situation. Now this highlights a key difference in different types of functions. Part A was something called an explicit function. This is a clearly defined function where y is all by itself. I mean, we know what y is doing. It's doing all this stuff that's happening to x over here. Part B is an illustration of something called an implicit function. This is kind of a hidden function. Here, maybe it's possible to express y as a function of x, but it's very tough to get y by itself and actually do that. So in today's lesson, we're going to figure out how to handle situations like part B, these implicit functions. In order to differentiate implicit functions, we're going to use something surprisingly called implicit differentiation. The key to this is we're going to differentiate the whole equation, not just the right side like we've been doing up to this point. And when we differentiate anything with a y in it, we are going to treat y as an inner function. Anytime we differentiate y, we're going to take the derivative of y, which is just dy dx. Now this is just using our friend the chain rule. If we treat y as its own kind of inner function, then we have this outer function of squaring. So this would be just 2 times y. But now if y itself is a function, we have to take the derivative of this inner function, which is dy dx. This is just the chain rule. Now don't forget to differentiate the other side as well. This is going to be equals 1. Next, since we're looking for the derivative of y, dy dx, we're just going to isolate dy dx. So that's just going to be 1 over 2y. Now the nice thing about this method is that even when it's impossible to get y by itself, we're going to find that we have a much easier time getting dy dx by itself. Another follow-up to this is that a lot of students prefer to write y prime instead of dy dx when they're doing implicit differentiation, and you can do that, but I do caution you it is very easy to mix up y prime with y. So I always write dy dx, but you do whatever you want. And you might be wondering now, well, if we have to do this with y, why don't we have to do this with x? Why don't we have to write dx dx after this 1 here? Well, let's think about this dx over dx. You actually could technically write this, but a number over itself is just 1, right? Another way of thinking about it, this would be saying the rate at which x is changing with respect to itself. Well, anything is always going to be changing 1 to 1 with respect to itself. So that's why we don't bother writing dx dx. Now that you've seen the basic process behind implicit differentiation, pause the video and get as far as you can on this problem. All right, let's see how we did. So going from left to right, we're going to, again, differentiate the entire equation. So this y becomes a dy dx, that is the derivative of y, minus, we'll have 3y squared times a tail of dy dx, equals, this will just be 10x. At this point, we need to isolate dy dx. Now, the way to do this is to remember that dy dx is actually a variable. It's a weird-looking variable, but it's a variable that represents the slope of y. So just like any variable, you can factor out dy dx and then divide later. So dy dx, we have one of those in there. We have another dy dx over here. Let's factor out dy dx, leaving us with 1 minus 3y squared. And now we can just divide by 1 minus 3y squared. And we've got dy dx all by itself. Now this is the reason that even when you can't isolate y itself, you can always isolate dy dx. Because of the way the chain rule works, when you differentiate everything that has a y in it, you will always end up with a dy dx that can be factored out. Just a quick note before we move on to the other problem. Another possible answer you could have gotten for this if you had moved things over to the opposite sides of what we did before factoring and canceling, you could have gotten negative 10x over negative 1 plus 3y squared. And this is actually okay. It turns out that fractions in which all the signs are reversed are equivalent, because if you think about it, you could just multiply the numerator and denominator by a negative 1 and get an equivalent fraction. So this is helpful to keep in mind if you're doing a multiple choice question and you see an answer choice with all opposite signs of what you have, you should probably pick that choice. We're going to do one more problem, and there are several curveballs thrown into this one. So first off, it's kind of a real-life problem. Derivatos, the fifth moon of the planet Calculon, has an elliptical orbit described by the following equation. So here's our equation, and if you were to actually graph this thing out, here's about what it looks like. We want to know what slope is the moon moving at for the point negative 1, 2, which is about here. So we need the derivative of this thing, dy over dx, and we need to figure out this derivative at a specific point. So let's start by getting the derivative. So derivative of x squared, that'll be 2x. So far, so good. And now we come to this negative xy term. So this term, it turns out, this is the product of two functions, and we're going to have to use the product rule on it. You can always use the product rule for any product, even something like 2x, but xy we especially need it. So let's set up the box and ribbon here, and I'm going to put this negative. I could put it with either one, but I'll put it with the x. So negative x, we've got y, and their derivatives, which are negative 1, and the derivative of y, dy over dx. So using the ribbon to multiply that out, I've got negative y, and then I have also minus x dy over dx. On to the next, derivative of y squared. That's going to be 2y using the power rule. But again, because we just differentiated something with a y, we have to use the chain rule. So we have a dy over dx tail. And finally, equals 7. Derivative of 7 is just 0. All right, well, same dance as before. Let's get anything in the dy over dx club on one side, everything else on the other. So on the left side, I'm going to keep this negative x dy over dx. This 2y dy over dx can also stay over here. And now moving over to the right side, I'm going to have this 2x, so that's going to be a negative 2x on the right side of the equation, plus y if we move that over there. Now we can factor out a dy over dx on the left, so that leaves negative x plus 2y inside. And now I'm just going to divide everything on the right side by this parentheses, so I have negative 2y, or 2x rather, over plus y over negative x plus 2y. Okay, now it's time for something new. We're going to plug in the point negative 1, 2. Normally we just plug in x values, but this time we're going to need two inputs because our derivative has places for x and y. And later on you'll see derivatives that even have a place for a dy over dx, but we're not there yet. So the way we show this is by writing dy over dx with a vertical bar. It's called a delimiter bar. And we have a little x comma y equals whatever the point is that you're plugging in. So going ahead and doing this, we have negative 2 times the x value negative 1 plus the y value 2 all over. We have negative 1 for that x value, and then plus 2 times that y value of 2. Evaluating this now, we have 2 plus 2 is 4, and then we have 1 plus 5, 2, or 1 plus 4 is 5. So that's our slope of the moon derivatos. Now, once you got to this point with all constants, you could, of course, not simplify it if it's a free response, but very often these are multiple choice questions. So at this point, we see the red stop sign here. The implication is that the lesson is over. Till next time, Mr. Sutton signing off.